Okay, so today we will start a new chapter, which is the first example that we study in this course, which is the bosonic case. And we study this lattice vibration or phonon in metals. And in particular, we will address this electron-phonon coupling and the BCSC reverse superconductivity. Yeah, to do this, let us just take a very brief review of these phonons in metals. And I believe that I have already discussed this in this previous semester, okay, Advanced Solid State 1. But let me just very briefly outline this phonons in metals. So those circles represent as ions in metals, and we have many electrons orbiting around this nucleus core. And this is our system and our Hamiltonian. And we know that these ions do not just stand there still, but they will move, they will vibrate, they will fluctuate. Okay, so the ions are sitting in the periodic lattice, but they will actually move back and forth with respect to this equilibrium positions, like this, because of this potential of ions. So, and I won't repeat that, this ionic potential, but there's an equilibrium position of ions that is sitting just at the bottom of this, a minimum point of this potential filled by the ions. And this is the equilibrium position of the ions. But at finite temperature, the ions may actually move near the bottom of this minimum point back and forth like a pendulum or like a harmonic oscillator. And this is the source of the phonon, okay, because the ion will change this equilibrium, this positions relative to the equilibrium positions, a little bit here and a little bit there, and correspondingly the electron ion potential will get modified, okay, and that kind of lattice vibration due to ions will couple electrons and ions. And the quantization of this lattice vibrations is called phonon mode. And we have discussed that in the previous semester, so I will simply just make very brief review of this phonon mode. But the key point is the electron ion potential and the coupling between electron and phonon. Okay, so this is the Hamiltonian of these electrons and ions. So this little p represents this electron momentum, and this is the kinetic energy of the electron, and this is the Coulomb repulsion between electrons. And for ions, this is the kinetic energy, and this VII term represents this repulsive interaction between ion cores. And there's a attractive electron ion potential. Okay, so you know very well that these electrons feel the repulsive interactions by Coulomb with another electron. So, but electron ions carry opposite charge. As a result, this electron ion potential is actually attractive, meaning negative. And for the same reason that this ion, since they carry the same sign of charge, so they feel repulsive interactions. Okay, so and this is our universe, or this Hamiltonian of the electrons and ions. And later we will derive this. I would review this phonon mode and also derive this electron ion potential when this ion precedes such lattice vibrations. Okay, so let me just continue. VII, this capital Z refers to the charge of the ion, and VEI. We could simply just review this phonon part, but we will do that in just a moment. As I mentioned, the ion may move a little bit away from their equilibrium positions like this. Okay, so let me just define my coordinate. This is the position of the electron, alpha, but once the ion got shifted to the new positions, center here, then the electron ion vector is got shifted as well. And this is VII, ion potential, and this shift is called U. Okay, good. So now let's just start to analyze this so-called harmonic potential or harmonic approximations for this displacement of ions. So this capital R alpha is the vector connecting some electron here and the ion core unshifted ion. And this shifted capital alpha is unshifted capital alpha 0 plus a displacement U. So you could very easily see the relation between this shifted and unshifted electron ion vector. So now let's just decompose this Hamiltonian in terms of electronic part and the phonon part and electron-phonon coupling part of Hamiltonian. So the electronic part of the Hamiltonian is given by the kinetic energy of the electrons and the potential energy or the Coulomb repulsion between electrons and the electron-ion potential and also the ion-ion potential. So let's take a short break. When we come back, we will continue writing down the phonon part and also electron-phonon part. Okay, so let's continue. So we have written down this electronic part of Hamiltonian, which I won't repeat here. So the second term is the phonon part of Hamiltonian, which is the sum of this kinetic energy of the ions and this harmonic potential of the ions, and this HEP represents electron-ion, this electron-phonon coupling. Okay. So the second term, this phonon part, is derived based on this kind of a harmonic approximation of this ion potential relative to this equilibrium position. So near this minimum point of this potential, we could approximate this potential of the ions by a second order in this displacement, R minus R0. So, and this is called second order approximation or harmonic approximation. So in terms of these variables, U alpha and U beta, this is just kind of a Taylor expansions of this potential near this minimum point up to second order in this displacement vector. Okay, so this phi nu here is simply just a second order derivative of this ion potential evaluated right at this minimum point. Okay, so and you sum over all these ion positions, alpha and beta, and nu is simply just components of this along this three-dimensional space, x, y, and z. And so the last piece is again, right? So the leading order when we make such a harmonic approximations, that the ion displacement vector U alpha will couple to the electron-ion potential in this gradient form. Okay, so this is, I should say, the first non-trivial order that the displacement of the ion will couple to the electron-ion potential, and this is the source of the electron-phonon coupling. Okay, so we will come back to this in just a moment. Okay, but this again, this is just a review. Everything I believe that is written here has been discussed in the previous advanced solid state 1. So now we should analyze this phonon and also electron-phonon part of the Hamiltonian by a Fourier transformation, and we Fourier transform this two pieces of Hamiltonian to the momentum space. And we also expand this displacement vector U alpha and this momentum of electron in a normal mode coordinate, and also subject to the periodic boundary condition. So this U alpha displacement vector plays a role as this position operator in quantum mechanics, whereas the little p alpha here represents the momentum operator. So U and P are conjugate variables in quantum mechanics, so you can Fourier transform this in K space. Okay, sorry, this P is actually the momentum operator for the ions, which is the capital P here. So let us just use this Fourier transform, this coordinate or displacement vector, and the momentum operator to re-express this harmonic part of the Hamiltonian. So capital Ni refers to the number of sites or ion. Okay, so we simply just plug in the Fourier transform of displacement vector and this momentum operator. And this harmonic potential now becomes the following. Suppose we defined the relative coordinate capital R as the difference between capital R alpha 0 and capital R beta 0. Then we could rewrite this summation over this alpha and beta in terms of the summation over capital R. This is relative ion position vector and capital R0 beta. Okay, so you simply just combine all these Fourier transformations. And we know very well that this, if you sum over capital R, e to the I k dot capital R is simply just the number of ion, capital Ni times this delta k0, which is simply by this periodic lattice, and this momentum is actually restricted to the first Bourgeois zone. So in that case, we could further simplify this. Okay, so remember this stuff inside the bracket looks somewhat familiar, right? So in this introductory level of the solid state physics, you know that this is for nearest neighbor harmonic potential, that this could be reduced to some kind of a constant minus this cosine of k. Okay, so remember that. Okay, but here, we'll come back to this kind of a different phonon modes, optical phonon modes and acoustic phonon modes later. But let's just formulate this in a more general level, and we will proceed by considering, the simplest possible approximation, which is the so-called the Jellian model, where you don't consider any lattice structure in your so-called metal, and then we will recover this acoustic phonon modes by considering the self-energy and due to the electron-phonon coupling and so on. So, but we could get to this phonon mode by considering a very simple model for this harmonic potential. Suppose we consider just kind of a one-dimensional chain of harmonic oscillator like this, and so they interact by this Hooke's law, where you have this quadratic in displacement as their potential, and for that system you could very easily get the acoustic phonon. So here we take another path. We consider no lattice structure in the beginning, and then we will find out this kind of so-called ionic plasma oscillation frequency, which is simply just a constant, say independent of momentum. But we know that this is too naive, and then we actually could go to the, say, higher orders to look for this electron-phonon coupling, and then this electron-phonon coupling will normalize both electronic band and also the phonon band. So when we calculate this renormalization or corrections due to the electron-phonon coupling to the phonon mode, and this acoustic phonon emerges naturally. Okay, so we will take the second pass. Okay, so in solid state 1, you are familiar with these two branches of the phonon mode, which we call this acoustic, where the omega is the low energy excitations of the phonon energy or frequency is linearly proportional to your underlying momentum, or this momentum transfer. And there is a higher energy mode, which we call this optical phonon mode, whose dispersion lies above this acoustic phonon. Okay, so if we simply to consider the low energy excitations of this electron phonon system, and we will take into account only the acoustic phonon mode, and we can forget about or neglect this optical phonon mode. Okay, but to get to the acoustic phonon mode, there are two approaches. One is here that I just drew here, that you could simply just use a simplest possible lattice version of the harmonic potential, which is the nearest neighbor Hooke's harmonic oscillator, and then you could simply just diagonalize this Hamiltonian of such a one-dimensional harmonic oscillator, and you get acoustic phonon mode immediately. Okay, or we will take the second pass right now, that we don't assume any lattice, at this point, and then we will get this ionic oscillation frequency, which is equivalent quantities to this omega here, and this omega is a constant if we don't assume any lattice in the beginning, but then we will take into account the electron-phonon coupling, which will modify in the self-energy to the, say, electronic band dispersion, also the phonon dispersion, and after considering the self-energy corrections coming from electron-phonon coupling to the phonon energy or frequency, then this acoustic phonon mode emerges. Okay, so the reason why we take the second part is because the self-energy corrections and the Green's function that we need to proceed in order to see this. But either way is fine.
Professor, I'm a little bit confused. If there's no lattice, what is your vibration? How to define the vibration mode?
Well, of course, this is a very crude approximation. You can consider, right, a bunch of, randomly distributed ions. Of course, the ion can actually move, even though there is no lattice. You could still consider more or less the ionic potentials described by this harmonic potential, which doesn't depend on whether you have a lattice or not. Of course, we know there's a lattice, but lattice assume there's no lattice in the beginning, and we could correct this kind of a too naive assumption.
So you mean, because you also talk about the Jelly model, so the Jelly model is a uniform testing background.
Yeah.
You talk about the random distribution of ions.
Well, of course, it could be uniform but random. So whatever you like to describe your system. So, well, we will come back to this in just a moment. All right, so if you proceed with the first part, you could consider the one-dimensional harmonic oscillator chain, and you'll get this acoustic phonon immediately. So, but, let's just do the second part. Okay, so let's take a short break. When we come back, I will proceed with this Jellium approximation. Okay, so let's just second quantize this, U and P, as we already mentioned in the previous semester, this quantization of the phonon mode from this harmonic potential term. So this U and P could be written in terms of a bosonic variables or bosonic destruction and creation operator and a dagger in Q space like this, where this epsilon lambda's function of Q represents the polarization vector of the phonon propagation mode, and this capital omega as function of Q and lambda refers to this phonon frequency, right? And lambda is simply just the direction of the polarization, which could point to x, y, or z. So this is a three-dimensional operator, and then we could use that second quantized fuse for U and P to rewrite this phonon part of the Hamiltonian, which consists of only this harmonic potential plus the kinetic energy of this ion. And we get to this phonon part of the Hamiltonian in the second quantized form, which is h bar capital omega times a dagger a plus 1/2, which is simply just summing over all this normal mode and normal frequencies of this harmonic oscillator of ions, and then you sum over this three-dimensional polarization directions. And to determine this capital omega or its phonon frequency, you need to really formulate this harmonic potential in the real space and the Fourier transform this harmonic potential in Q space. Remember that, right? So you need to really have such a lattice version of this harmonic potential, and then you Fourier transform this and Taylor expand this up to second order, and then you need to, in the realistic lattice version, you need to find this determinant of this big matrix, because this is as a very big matrix that you need to find out this determinant of that big matrix, and the eigenvalue of that big matrix corresponds to this phonon frequency capital omega. So far there's no other assumptions rather than the in addition to this the second order or harmonic potential type of approximation. So from now on we should make another assumption to simplify our calculation, and this assumption is so-called the Gallium model, where we don't have any lattice structure in the problem, and these ions are distributed in a uniform weight and without any lattice structure, which means that now our reciprocal lattice vector G is simply 0. Okay, I guess probably time is up for today. So up to here, there's still the lattice. So, and start from here, we will further assume that there's no lattice from the start. And from this so-called Gallium approximation, we could get this capital omega, which is simply just a number. So let me just write it down. Capital omega squared, where the little vc is the volume divided by the number of ion, which is the so-called the volume, average volume per ion. Okay, so little vc. So we will get back to this next time. And then we will start to correct this kind of a too naive constant phonon frequency results by considering the electron-phonon coupling, and then you will get this acoustic phonon dispersion after this self-energy correction. Okay, so I'll see you on Tuesday, right? Tomorrow.